Okay, are there any questions? You can hear me, yes? Oh,
Yeah,
can
yeah,
you
we
hear
hear
me?
you. Yeah, of course.
Okay, so let's talk about limits. So we talked about products and like x times y. We talked about fiber product, and we talked about the dual notions of coproducts and push-outs. So now we can talk about limits. Limits is generalization of products, fiber products, and final object, terminal object, and plenty of other stuff. So there is some really frustrating things problem here with the terminology. There is an old terminology and new terminology. Old terminology use direct limit, direct limit, and they are like denoted like this, and inverse limit, which denoted like this. In new terminology, this is called limits, and this is called collimate. So of course you want to hang the person that invented it. So I don't know who was this person, probably more than one, and there is some excuse for this horrible terminology. And so the point of view for limits, like generating, so the main special case of limit is product, and the main special case of colimit is coproduct, which kind of makes sense. The only thing is that coproduct also sometimes called sum, because in vector space coproduct is direct sum. And remember that direct sum and direct product is not exactly the same thing. If we have infinitely many objects, and it's in infinitely many vector spaces, kind of opposite or different. So okay, so the notion of limits came from generalization of this, and this is why they use no, the word limits for generalization of products. And when we want to talk about coproducts, so the generalization will be colimit, so it's make more sense. Um, but from another point of view, like direct sum is maybe more basic than direct product, so it made more sense to call it direct limit. And you will see in a moment why it kind of makes sense to call inverse limit actually inverse limit. So both of terminology kind of make sense, but both of them together does not make any sense, and this is what we stuck with. Okay, so to limit is something that you take off a diagram. So you have a diagram D, and then you can talk about limit of D, um, which in all terminology is denoted like this, inverse limit of D. And maybe we'll start with the most basic example of diagram, like this: A0, A1, A2. And here we can put 0. So you see that this diagram look a little bit going inverse, and this is the reason why it's called. So this is a basic kind of diagram which you take limit of. So this is the reason why you sometimes call it inverse limit. So you have this diagram, and now in some category C, basically this is a shape of diagram. This is a graph, and in any category I can consider diagram of this shape. And now I consider a new category. So let's call it, I don't know, C. Yeah, it's a kind of over category of the diagram D. So this will be the diagram D. And what are object of of the CD? So those are diagrams of the following form: 0, 0, B. Commutative diagrams of the following form. So you remember we talked about it, that we often would consider commutative diagram of a given shape, and moreover we have a subdiagram there of which is actually fixed. Not only its shape is fixed, but the actual subdiagram is fixed. And Yes, so this is, let's call it phi0, phi1, phi2, 1, etc. So what are morphisms in CD? Those are also morphisms, maybe I should write like this, morphisms in CD between two diagrams, one which is given by the set B and phi I, and another which is given by the set B prime and phi I prime. So you can guess what it is. We basically, we write those two diagrams together. So we like morphism between diagrams, but we remember that the AI are fixed, so we don't put there any morphisms. So if we want to put there morphisms, we just put identity. So we have A0, 0, B and B prime, and we have morphisms like this. So we have a diagram like this, which we want to be commutative. Um, so if you want to be a little bit more formal, you want to have maps. Let's write it a little bit more formally. Collections of maps Ci. No, sorry, not just one map. Sorry, Psi from B to B prime, such that this big diagram is commutative, and let's write it explicitly. You can first perform Psi and then perform phi I, or first perform, sorry, or just make phi I prime, and this should be equal. So is this definition clear?
Yes. What is a zero? Zero.
Ups. Yeah. Just ignore it. Let's consider just finite sequences like this. Yeah, I'm used to think about a billion categories, but okay, so this definition was for a very specific shape of a diagram, but you just can repeat exactly the same definition for diagram of any shape. Just instead of having sequence like exactly the same definition, meaning this definition, if you want to write it explicitly, you will have to write explicitly whether it means that the big diagram is commutative, but yeah, you can do it without any problem. Yeah, so usually you start with the limit of a commutative diagram. You probably can do it for limit of non-commutative diagram, but there is not too much sense in it. Oh, you wanted to ask a question? Okay. So let's do some example. Let's consider diagram of this shape, which means just two objects, x and y. And consider the limit of this diagram. Any guesses what will it be?
Anything? Because there is no restriction.
What?
There is no restriction, so anything?
You kind of know the an answer to more complicated questions, so you answer in terms of in terms of something more advanced. So what do you mean by anything? Limit is some specific object, or in fact, many objects can be called limits, but they're all the same. Sorry, I didn't say what's the definition of limit. I'm really sorry. So limit of the diagram D is the terminal object of this category C. So you can think about this CD like the over category of the diagram D. Object together with a map to each object in the diagram D. So what will be the limit of this diagram? So Tal, maybe you want to explain what you meant when you say everything?
No, I'm not sure. Wait, I need to think.
So maybe we should first understand this category CD.
Hey,
So it's actually a category that we saw before. In this case of this diagram. Any guesses what is this category?
Object with two morphisms, one to x and one to y.
It's category of diagrams like this when here you have x and here y. So you remember what we called this category? I think we denoted it CXY. So what is the terminal object in this category?
what is B here?
Product.
B is like running. Yes, but somebody said the correct answer. You consider a collection of such things when x and y is fixed and b is running. So
Okay.
somebody says product. Who said product?
I did.
Okay, so you was right. X times y. So the limit is a terminal object in the category of such diagrams, which is by definition the product. Again, if it exists, yes. Okay, now let's do another diagram. X, S, Y. What is the limit here?
Fiber product.
Fiber product, exactly. So we saw that product and fiber product we can get. We can also get infinite products and infinite fiber product. So now let's go. What?
How is it? It's just related to the sequences
So
before?
sequence is just an example of a diagram. What happened here? I don't know. Oh, no. So D was a diagram here. This was a diagram D that looked like this. So I wrote the definition in this example because this is kind of a canonical example for inverse limit, which also called projective limit sometimes. So it's called limit, projective limit, and inverse limit. But we will go in a minute. We will go to this example again. But then I said that you can do it for any diagram, and then I wanted to do for some other diagrams which does not look like a sequence. These are the two diagrams that I wanted to analyze: diagrams that look like 2 points, and diagrams that look like 2 points, 3 points, and 2 arrows.
Okay, thank you.
Okay, so now let's go to back to sequences, but let's talk about in sets. Let's see, be the category of sets. And we have this diagram. So I will call it A. I forgot A1, A2. So I never promised you that limits exist, like product and co-product and fiber product. Nothing is promised to exist, but in specific categories, many things exist. So I claim that if you consider this diagram and you consider the category to be sets, then the limit exists. Any of you can try to describe what it's going to be? Or maybe it's not really a fair question because if you saw a limit before, you probably see this thing. Or you saw inverse limit, you see this thing, and otherwise not. So, limit of this diagram. I will write. So again, you do the usual abuse of notation. So limit of a diagram, for one hand, it's an object in the original category. It's probably more correct to consider this object together with maps to the objects in the diagram, or in other words, object in a different category, object in this category CD. And in that category, the limit is terminal object, so it's unique up to unique isomorphism. In the original category, it's it's unique up to an isomorphism. This isomorphism is not unique, but it is canonical in the sense that if you require this morphism to be actually morphism here, which is basically a property of morphism in C, then it becomes unique. So it is canonical. So when I say what will be the limit of this category in sets, I would just describe a set, but it will be implied that this set is equipped with maps to each of these AI. And the set is like this. So first of all, you consider the product. So the product is all sequences like this. But you don't consider the entire product, you consider a subset of the product. So here now I'm allowed to talk in this language of set theory, so take elements that satisfy something. This we will never do in general category, but in the category of sets and in other categories similar to sets, we can do it. Such that what is satisfied, so phi I of AI is equal, whatever there. No, I did the wrong direction of arrows. What I could have right now would be correct, but boring. Phi I of AI equal to AI minus 1. Of course, I should be larger than 1 in order just to make sense. Yeah, did I do before the correct? Oops, the correct direction? Yeah, before I may have the correct direction. We can also add this A0. And here. So, is this definition clear?
It's only in sets, right?
Yes.
Okay.
And maybe another thing that I have to say, so limit is, as I said, is an object in the category, but it also have to be equipped with maps like this. And in this case, it's clear what are the maps, it's just projection to the i's coordinate. And this is the original example of like projective limit. So usually it was done not in sets, but in some categories that are like categories of sets that have some additional structures, like vector spaces or something like this, or abelian groups. So you probably would see it as a definition of inverse limit of groups, or first time, or abelian groups, or maybe vector spaces. And you see it kind of, it takes some time to get used to this definition. So you see that most of the information here is unnecessary. In fact, any specific bit of information here is unnecessary, because if you know an, you don't need to know all the previous a's, because they're all determined by an. So you can erase from this sequence any finite chunk, and the limit will not change. And this is something that you're used to when you talk about limits, because limits is something that doesn't really, like in analysis, limit doesn't really care about finite chunks. So it makes sense. But
Rami,
yes.
I'm just want to clarify the direction of the arrows. You say this, you're looking at the category of diagram, but the arrow is inverted, right?
What?
Because
What? 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 I don't
the
collect diagrams.
the diagram here is only the sequence, right?
And the arrows,
yes, and the
which goes
but
like
the
this. So the
but we
arrows
said
go forward, but the indexes goes backwards.
yes, but we said that the direction of the arrow in the diagram category is in the other direction. It's
What?
morphism.
What? What? The diagram
Okay,
category.
no?
The arrows can be in any direction that you want. No,
In
the arrows in diagrams can be in any direction that you want, because it depends on the shape of the diagram.
yes, but from the in the objects in the diagram category are morphisms. Um,
Morphisms are just morphisms between the diagram. But in
yes,
this
but
case,
the
we're talking.
objects are with the other direction of the arrow, right? The objects are um, equipped are
I
an
see. I
object
wrote here
equipped
not
with
good.
a
Sorry.
different.
If I want a map from B to
Oh.
B prime, I want a map from B to B prime, not from B prime to B. It was a mistake. Sorry. Is this what confused you?
No, I we just said that we look at the morphisms from the diagram to the objects B or such. Because
No. From
the other
B.
way.
So CD is categories of that look like this. From B to the diagram, to the objects of the diagram.
Okay.
It's kind of the over category. I wrote B downstairs, but it's still over category. It's the over category of the diagram. You, you have this notion over. You have over category of an object, and you can also discuss over category of a diagram.
Okay. Thank you.
So if you have diagram of this shape, this is the notion of in sets. This is the notion of limits. Limit. All the sequences of AI, such that when you go forward, you get like go to the right. I don't know what is forward now. You get the previous AI. So the beginning of a sequence is determined by the end, by anything there later. Yeah, so maybe the best known example of an inverse limit is z hat, or even zp hat, or zps. So this is the inverse limit of z modulo z n times z. And you also have zp, which is the inverse limit of z modulo p to the k z. Yes, so how you describe an element here, you first of all describe number modulo p. But then you want to refine it to lift it up to its representative modulo p square. Then you refine it further to representative modulo p cube, etc. Yeah, so again here, like define an element in the limit is choosing element here, refine it to an element here, like consider this map. If this map is onto, then choosing element in any one that maps to a element in A0, it's always possible. So you can always start with element A0 and refine it further. If it's not onto, it means that the element that you start with, that you choose at the beginning, have to lie in all images. And then when you refine it to element here, it also have to lie in all images. Okay, so here there is an exercise. I told you what is the answer, but I did not prove you that this is the answer. So I did construct a set with the candidate for the limit, let's call it B, and I did construct maps like this, but I did not prove that this is a terminal object. So exercise for you to prove that this is a limit. That this is the okay, so when we write inverse limit, projective limit, we usually think of such diagrams: infinitely many objects and maps to the right, and the object goes to the left. Or like the map goes to one direction and the infinitely many object goes to the other direction. But we don't, okay, it doesn't have to be like this. For example, we can take inverse limit of this diagram. A0, A1. And anybody have a guess what it is?
A0?
A0, exactly. Because A0 naturally equipped with maps to all of the other objects. And anything that have maps to all of the other objects, such as the diagram is commutative, basically have maps to A0. So the over category of this diagram is just the over category of A0. And the terminal object in this over category is going to be just A0. So you can do other shapes, but sometimes you can get an boring answer. Okay, so another exercise. Limits always exists in sets. So in the category of sets, all the limits exist. Basically, the construction is very similar. I can give like the main hint here. You have some diagram D, which consists of objects AI and some morphisms psi whatever. So limit of D is always a subset in the product of all AI. So you have to choose element in each AI such that something will happen. And something that will happen is that each time that you have an error, the element that you choose at one object should go to the element that you choose in the other object. So the most natural thing that you can think of. So this is a notion. So this is a construction of limiting sets.
I have a question.
Mm-hmm.
If no such a sequence admits all the requirements, so the limit is the
Yes,
empty set, or
yes.
okay.
We probably can find, yeah, you can find easily an example like this. In a moment, I would say a special case of limits. Okay. So as you see, limit is something very general, and all the categorical notions that we had before, and in a sense, all the categorical notions in the world can be expressed via limits. They're all limits of something. So, for example, terminal object is limits of what?
It's the limit of a diagram with a single point.
Even worse. Another attempt.
Initial object, maybe.
But maybe we don't have the initial object, so
Diagram of one point.
The limit of an empty diagram.
Exactly, yes. The limit of an empty diagram. If you have an empty diagram, so the over category of the empty diagram is the original category. Then you need, if you have an empty diagram, so what is the over category of it? You have B and map to each object in the empty diagram, which means that you don't have to specify anything because there's nothing to specify. So the limit of the empty diagram going to be the terminal object. So everything can be expressed via limits, even the notion of a terminal object. On the other hand, you saw that in a sense everything can be expressed via terminal objects, because limits are terminal objects in some diagram. Okay, so, and as I said before, in category theory, each time you have one construction, you also have the dual construction. So you have the notion of collimate, which is a limit of the same diagram, but in the opposite category. And here, it will make more sense to consider diagrams like this. So A0, A1, etc. So the co-limits of this, which in old notation called direct limit. And in new notation, you just write co-limit, but whatever. So now I didn't promise that the co-limit will always exist in sets, but still you can try to guess what will be the co-limit of such diagram.
Sequences where all the objects in the sequence are mapped by the morphisms of the
So this will be the
category.
limit of such diagram, but if we have such a sequence, so this sequence will be determined by an element here. So we want something a little bit different. So
shouldn't it be A0? Wouldn't it
so
be
the limit
A0?
of this diagram will be A0, but the co-limit will be something a little bit different. Oh, in fact, a lot of different. So maybe we can first think about the case when all those maps are one-to-one. So we're talking about sets yet. So consider all those maps are embedding. Then will you have some guess?
This is the union.
The union, the ascending union. And now if you try to formally define, oh, okay, you always get, okay, like even for, let's do in set theory. So in set theory, we have the notion of usual union, but it's, so nobody said to us that this embedding is actually the embedding of a subset to a superset. So it can be just one-to-one map. So if we just take the usual union, it will be bad. We first have to somehow identify things. So how we formally define ascending union in set theory?
Product.
Just a coproduct will mean that we take all of the AI to be disjoint. So we can start with the coproduct of all of AI. Yes, but then all the AI are disjoint. But when you take ascending union, you don't want to think about all AI as disjoint. You want to think, you want something different. Yes.
You can take the direct sum, but modulo the equivalent relation that if two objects are mapped to the same object, then they're equivalent.
If those all guys are embedding, so two objects never map to the same object, but you probably meant something else, almost the same. So some equivalent relation. So we talk with, so it doesn't call it isn't called a direct sum here because we're talking about set. We're talking about coproduct, so just disjoint union of all of AI. And now we want to consider elements in A0 as if there was also elements in A1, even if a priori they are not the map. So the map here is some like phi0, some map, but let's assume for a moment it's one-to-one. So I want to consider phi0 of A to be the same as if as A, and in general phi I of an element A. So for all A in AI, I want to consider those two things are the same. So this is not an equivalence relation, but it generates an equivalence relation, and I quotient by this equivalence relation. And now I see that once I wrote it down, it completely doesn't matter that those maps was embeddings, and it completely doesn't matter that this diagram was of this shape. So this is definition, the construction of definition, the construction of the co-limit, of the direct limit for arbitrary diagram of arbitrary diagram of sets. You take the coproduct, just disjoint union of all these sets, and then you start to glue things one to another. Each time you have one element that go to another element, you declare them to be the same. So last time we took product, we took choice of elements in each guy, and then we demand them to be the same. This time we do something dual. We take coproduct, and we don't demand them to be the same, because in coproduct they will never be the same. We declare them to be the same. We force them to be the same by quotienting out by equivalence relation. And of course, a priori this is not equivalence relation, but it generates an equivalence relation, and this is it. Okay, so we defined limit and co-limit. We proved, okay, now exercise. Prove that that column exists in sets. So I told you the answer for this exercise, what is the co-limit, but now we have to prove that it actually satisfies condition. Okay, so now another important example. What happens here? Of co-limit, or of limit first of all, it's called the equalizer. So if you have two objects, x and y, in some category, and two maps, phi1 and phi2. So you can consider this as an equation. if x and y would be sets, so you can consider the equation where phi1, sorry, equal to phi2. And the set of solution of this equation called the equalizer of phi1 and phi2. And this is exactly the limit of this diagram. So the limit, again, the inverse limit or just limit. So it is the equalizer of phi1 and phi2. So as I said before, the equalizer exists, sorry, limits exist in sets, so equalizer also will exist in sets. And being, so you know that it exists, but now an exercise a very simple exercise just to compile what I said before. Exercise compute equalizer in sets. So the answer is what I said. It's a collection of all elements in X such that phi1 of X equal to phi2 of X. So this is a notion of equalizer. And of course, there is a dual notion of co-equalizer. So I can make this exercise more complicated by asking you to compute co-equalizer. And co-equalizer, it's really an harder notion. It basically will be, you take X and you quotient it by the equivalence relation generated by the condition that two things are the same if, no, you take Y. I think you take Y and generate by and quotient by the equivalence relation generated by the conditions that two things are the same if one of them is phi1 of X and the other is phi2 of X. So you glue things in Y. And since it's equivalence relation generated by something nice, it by itself something which is not nice. So if X and Y would be topological spaces, then co-equalizer will not always reasonably exist, or it will not always be Hausdorff or whatever. Yes, so co-equalizer, it's a weird construction as opposed to equalizer, which is nice construction. In day-to-day examples, of course, from point of view of category theories are completely equivalent because you can take just the opposite category and this is it. Okay, so before there was a question whether it can be that a limit is an empty set. So the answer is yes. If you take equalizer, if you try to solve a system of equations that does not have a solution. So exactly, this is the case when you get, well, a case when you get an empty set. And okay, I still have 5 more minutes before the break. So you probably notice that, so I gave 2 constructions of limits and co-limits in sets. And they was based on the fact that we have product and then we have some equation. So there was based on the fact that we know how to solve equation or have a notion of let's solve an equation and have a notion of product. So notion of let's solve an equation meaning equalizer. So it should give you a hint for the following theorem, which also will be left as an exercise. I will give some hints, but that let C be a category with products and equalizers. Then C have limits. So if we have a category which admits products, so that products exist and equalizer exists, then it have limits. So here I have to be careful. What do I mean by saying product exists? So product, I said product you can take for any collection. So do I mean for any set in the world, or how big can be the diagram? So usually we want to bound somehow the diagram. So this statement is true basically for any cardinality separately. So you can talk about finite, if it's a finite limits, then it's have finite products and equalizers, then it's have finite limits. If it's have limits of cardinality up to some cardinality kappa, and sorry, if it's have products to up to some cardinality kappa, it's the end equalizer, then it have limits up to the same cardinality. So you usually want to fix the cardinality because you probably don't want if your category is small, you don't want to consider a diagram which is larger or close to the size of the category itself. If the category is a set, so it has some cardinality by itself. Sorry, I killed the camera. Okay, so the proof is basically the same construction that we had before. You first take the product of all the objects, and now you will look to the, you have some diagram D, which constructed from some vertices, some objects AI, and some morphisms. So you take product of all the AI, and this exists in your category. And now here you will look for the limit, so it has to be solution of some system of equations. So you have to find two morphisms to some other object, which also will look like product of something, but it will be larger product because so you have an equation for each morphism. You have a variable for each object, an equation for each morphism. So you basically take product of also of the same AI, but with some multiplicities, which coming from the fact that you have many errors. And then you write your equations. So you have this theorem, and this theorem, of course, of its dual version. If you have co-equalizers and co-products, then you have co-limits.
Is the process of generating the solution is finite? I mean, isn't it possible that you need an equalizer for every morphism such that
yes, it is fine because you can cheat. Because when you have infinite system of equations, you can write it like one big equation. Because I never say what the target is. The target can be also infinite product. You write the first glance, you think, okay, you take you write each equation, you give you some equalizers, and you write second equation, another equalizer. But you can pack them all together in some one big equation. Okay, I will tell the solution if you will want me to, but maybe not this time, but next time, because I want you to think about it before. Or maybe Guy will tell it. It's not hard, but it's not completely obvious, so you can do it in 10 seconds, usually. Okay. And what I want, so and of course, if you want only finite product or only finite limit, so it's enough to have product of two objects, because once you have product of two objects, you have any finite product. And now there is another nice thing that I will probably talk about after the break, is that even equalizer is kind of weird. Fiber product looks more natural, so you can replace equalizer with a fiber product. So sorry, but if you want finite products, then so product of two objects is not enough in order to get all finite products, because it will not give you the empty product. So you need finite product, two objects, and the empty set. Empty product. Empty product is just the terminal object. So you will assume that you have terminal object. So another theorem exercise, that if one C have terminal object, 2 C have fiber product, 3 this is it. Yeah, this is enough, more or less. Let's do the finite version. I'm sorry. Oops. Let's do the finite version. C of two objects. Then C have finite limits. Okay, so let's make a 10-minute break and continue afterwards. I'm leaving the room open, but I mute myself. So do you have any questions? We still have 2 minutes. Ah, but you probably all away. Okay. So I still have 1 more minute. When I got Okay, so who is back? Can you do some digital hand raising or physical camera owning? 1, 2, 3. Okay, still 4 of us are not back. Oh, no, not 4. Oh, most of the people are not back. Only 4 are back. Oh, 5 are back. But we're already 1 minute late, so we probably can continue, but maybe we'll start with questions. Do you have any questions? No questions?
I have a question. Is the initial object a limit?
No, it is a collimate.
So when you say that every categorical construction is a limit or collimate, is a limit you meant limit or collimate, right?
Yes, but you can also say the collimate is a limit in the opposite category, so it is also okay. So it is also a limit, but in different categories. Okay. So a hint to this exercise. So how you can express things via like a fire product is also a solution of equation f of x equal to g of x, but it's not. So f of x equal to g of y. So it's look like if you will add to it the equation x equal to y, it look like something that will give you a general equation, and indeed you can get from fire product any general equation, and the way to do it is to use a diagonal map. So you have x times x. So you have a map between x to x times x. That's called the diagonal map. And this is very simple. So intuitively, it's just a diagonal map in case of sets. So you have x times x, you have the diagonal, and x is mapped to the diagonal. But the definition comes here from the fact that you have this diagram, identity, and since the product is terminal object in all such diagrams, this gives you a unique map like this. And this unique map is a diagonal map. So this is a nice construction to use. And of course, there is also the dual notion of co-diagonal map. So it's an exercise to think what is a co-diagonal map in some nice examples. But this is it. Okay, so we have limit, Collimate, equalizer, co-equalizers, and we know that everything can be written via equalizers, or limits can be written via equalizers, and equalizers in their turn can be written via fiber products. So basically, everything can be expressed via lots of fiber products. So yes, another universal thing in category theory, almost universal thing, is a fiber product with which you can more or less express everything. Okay, so now I want to start the second topic. So until now, it was a plan for the first lecture. I'm 2.5 times slower than I thought. So the second topic is abelian categories. And this is some nice thing about category theory, that category theory, okay, the notion of categories itself have some structure in it. But the thing is that you don't really, in many cases, you don't really need to add more structure. If you add enough conditions, you kind of gain new interesting structures for free. And the best example is in additive and abelian categories. So first of all, let's define the notion of zero. Yeah, so what is a zero object in the category? A zero object is an object which is both initial and terminal. So of course, if it exists, it's unique. So another way to phrase it is that we say that a category have a zero object if it's have an initial object, have a terminal object, and the natural map between them is an isomorphism. Yeah, so you always have a natural map between the initial and the terminal. So if this map is an isomorphism, which is just equivalent to say that there exists a map to the other direction, then we call both the initial and the terminal object zero. So now, if we have coproduct, now, okay, here it's just discussion, so I don't know how to call it. So suppose C have zero. Maybe before this, if we have so this was the definition of zero object and definition of zero morphism. So what is zero morphism? Is any morphism that factors through the zero object. So any composition like this called a zero morphism between x and y. So, and you see that if you have the zero object, then you always have a unique zero morphism between any two objects, x and y, because you always can construct, you always have a unique map to zero, which is because zero is terminal, and unique map from zero because it's initial. So now suppose that C have object of zero. Now we have x comma y, and now I want to construct some canonical map from here to here. So you remember that in the case of abelian groups, we have an isomorphism between coproduct and product. In case of general groups, coproduct was free product, and product was just direct product, and we also had the morphism, which is not isomorphism. In case of sets, and we didn't have any natural morphism between them. In case of pointed set, we did have map between the coproduct, which was like a packet, to the product. So, and now we see that in case of sets, we don't have 0. Set does not have 0 because empty set and singleton are different objects. But in all other cases that we discussed now, pointed sets, groups, and abelian groups, we always have 0, and this is why we do have such a map. So let's construct this map. So what does it mean to construct a map to the product? It's the same, by definition, it's the same as to construct a map to X and a map to Y. So we need to construct a map from here to X and a map from here to Y. So what does it mean to construct a map from a coproduct? By definition, it's the same as to construct a map from X and a map from Y. So, okay, now I see that okay, maybe not that. X. Yeah, so we have a canonical maps like this. And if we will construct two maps like this, then we will have a unique map like this. Oops. So we do the only thing that we can do. Here the natural thing is to put identity. While here, between Y and X, we cannot put identity. There is only one natural thing that we can do. We can put 0. Yes, so I can write here the same thing. Y, here X. So let me erase this. So here I want to put identity, and here I want to put 0. And this will give me a unique map from the coproduct to Y. And those two maps, this one and this one, will define a unique map from the coproduct to the product. Oops. So basically, if we, yeah, so there are specified arrows here and unspecified. Let me write specified or specified. This, let me call it IX and IY. IX, sorry. This is IY. Yeah, so the coproduct is equipped with two embeddings that we will denote IX and IY. And the product is equipped with two projections, which we will denote per X and per Y. So this is per X. So some maps here in this diagram are specified, and basically the claims that by definition of product and coproduct and 0, and there exists a unique way to complete this, all the unspecified arrow, to such that the diagram will be commutative, and in particular we get a map between like this vertical map. So maybe we'll call it by some name. I don't know, phi. Yeah, it's ad hoc name. I don't know how it's denoted in the literature. I don't want to specify it in the diagram because it's unspecified. So we define this map to be the unique map, the unique vertical map, such that there exists a commutative diagram like this. So now
Again,
definition.
what are you assuming from this diagram, that it
It is
like a
commutative.
hybrid product?
I assume that C have product, co-product, or at least X and Y have the product and co-product, and I assume that the C have 0. And on this diagram, I assume that all the specified map are what they have to be. So all the maps that I wrote annotate in some way, they are specified. Yes, so the projection to Y, projection to X, embedding from X to the co-product, embedding from Y to the co-product, the 0 maps in some places, the identity maps in some places. So this I'm specify. What I do not specify, so maybe I will choose another color. I can do it here. Yes. So I not specify the red ones. No. Yes. Yes, okay. Yeah, so the red maps are not specified. And the claim is that there is a unique way to specify them such that the diagram will be commutative. And this just follows, I just explained it, yes, it follows from the definitions of product and coproduct. And once you specify them, or once you get them, you get also this map from the coproduct. Yeah, maybe I will write it from X coproduct Y to sorry. So is the definition of this map phi clear? So maybe I should say in examples, let's do pointed set, for example. So I already said what is phi in this example, this embedding of the cost to the plane. But you can ask what is this map from the coproduct to Y. So basically you take Y and map it to Y's identity, and then you take X and collapse it to one point at Y. What one point? If we're talking about pointed set, we have the specified point in Y. And this is the reason why we have this zero map. Okay, so now definition. So I think it's semi-additive category, but I might be wrong here. It might be pre-additive. It makes more sense for it to be semi-additive. Semi-additive category. But better to Google it. Sorry, I didn't prepare and didn't Google it, but better you can Google it and check whether it's the definition of semi-additive or pre-additive. Is a category with 0 product, coproduct, such that the natural map between the product and coproduct is isomorphism. So this is just a property, it's not a structure. But we already saw that also having 0 is just a property, but it gave us some structure. Now morphism map between any morphism sets between any two objects become a pointed set. And here, once we have this structure, and this property, I claim that we gain much more structure. I claim that the morphism set of between two objects become a semigroup. So let me explain the structure, and the exercise will be to prove that it's actually a semigroup. So we have phi from X to Y. Not only a it's commutative semigroup. And psi also from X to Y. And now I want to define their sum. So I did not prepare, so I hope it will work well. Yes, so the idea is that I get a map from phi from X. So I have two maps from X to Y. So it gives me a map from X to Y times Y. Yes, by definition, if I have a diagram like this, phi psi y y. Yeah, I can call it phi times y. Psi, it's a unique map that makes this diagram commutative. No, I'm wrong, sorry. Yes, now I'm correct. So the unique map that makes this diagram commutative, let's call it phi times y. So I had a map between coproduct and coproduct. Oh, sorry.
What are all the arrows?
some of them are already specified, and here I
This
can put
ID?
identity. Now it's good?
Yes, thank you.
Yeah, so you think about sets, you have two maps from X to Y, so you get map which first coordinate is phi and the second is psi, and together they give you a map like this. Now we had a map like this, and here we have map to Y. Yeah, again, if you think about sets, Y coproduct with Y, so you have natural map to Y. And let's see why it works, how it works. This is a codiagonal map, yes. I don't know how to call it delta bar. So we have Y, and we have just two map like this. We have, no, I don't want this, I want this. By definition of coproduct, where it's equipped with two maps like this. So now there exists and unique. This is an initial object. There exists and unique map like this. So let's call them with names. Yeah, oh, sorry. Yeah, I wrote the identity, but I didn't mean to. It should have been Y times Y, and here was per 2, and here per 1. And here I also want to say, so here it's identity, identity, the first embedding, the second embedding, and the codiagonal. So you have a diagram, a sequence like this. X maps to Y times Y. This you have in any category is product and coproduct. But our category is semi-additive. So this is an invertible map. This was like phi product coproduct, I don't know, bad name, but whatever. And here we have the inverse of this map. It's invertible, and the inverse is unique, of course. Yeah, it's something that has to be proven. So if you have an isomorphism, then the inverse map is unique. So it's very simple exercise that should have given in the first lesson exercise. If phi is iso, then phi inverse is unique. So there exists a unique isomorphism to the other direction, such that both compositions are identity. So you know this exercise in group theory, if the inverse exists and it's unique, so it works the same here.
What is delta tag just?
Delta
Delta
bar.
gag bar.
Yeah. And so this is a codiagonal, and here is a definition. It's a unique map that makes this diagram commutative. And it exists and unique because of the definition of coproduct. And intuitively, you have Y coproduct with Y, which is kind of disjoint union, so you just put them together. But of course, this is example in sets, so this might be defined not only in sets. So in sets, this is the way defined, but sets cannot work. Sets is not semi-additive, so we don't have this inverse. And in fact, we even don't have phi. If you just do sets, you don't even have phi. With this phi product from coproduct. If you work in pointed set, you will have phi, but it will not be invertible. So in vector spaces, for example, it's a nice exercise that the codiagonal is just a sum. And so it makes sense when you want to sum two morphisms, you first of all just take their product, you get a map from X to Y times Y, and then sum them up and get a map in Y. Okay, so definition, phi plus psi is this composition. First you perform phi times psi, then you perform X cap, this map between product and coproduct, but in the opposite way, and then you perform the codiagonal. The codiagonal of y. So exercise is a semi-group structure, or in fact monoid. Monoid structure on more xy. So if you have in a semi-additive category, sometimes it's also in general categories, but just another name for more that often used in semi-additive case is HOM. Mo is short for morphisms, and HOM is short for homomorphisms. In fact, morphisms is short also for homomorphisms, so it doesn't really make too much sense, but somehow traditionally it's more common to use the word homomorphisms for categories of algebraic nature when you can add things, and morphisms for category of, say, geometric nature, so, or other nature, so whatever. And maybe another exercise, describe for vect abelian groups, and maybe something else. And maybe another exercise is always a group structure. So the answer is not, it's not always a group structure. It's always a monoid, but not always a group structure. So the zero element is a zero-morphism, but you not always have negative antipode. And exercise to find an example. So any questions about the definition of this addition structure on morphisms?
Is it abelian?
Yes,
Is
it's
it
yes, it has always exercise is commutative monoid structure. More questions? No more questions. Good.
Is there is it possible to define similarly addition in the objects and not only on the morphisms?
You have the product and the coproduct, which you can call direct sum. So good question. Definition: if C is semi-additive, we define direct sum to be the coproduct, or if you want, product. Yeah, so often you have a definition of a additive category. It's a category with this additional structure of having a group structure on morphism, abelian group structure of morphisms, but it's not. So if you put all the conditions, then it's not actually a new structure. So basically, you can, from the conditions that I already said above, the semi-additive categories, you can reconstruct, you can define the structure of addition. So
but only for finite ones, right? Finite collection.
So when addition, I talked about addition of morphism. So of course only for finite, but from object you have coproduct and you have product. You can do them from infinitely many objects. They coincide only for finitely many objects.
Yes, but you define them in both ways. So you should do
So
this only for
direct sum
finite.
is something that's defined only for. Okay, you know what I can do. Direct sum is only for two, but okay, sometimes we use it for lots. So just let's put it like this: direct sum is a coproduct in semi-additive categories. In not semi-additive category, you don't use words direct sum. Usually you can use them, but it's not common. Okay, definition: a semi-additive category is called additive if hom xy together with this addition is a group. So if you have antipode. Examples: vect, abelian groups, topological vector spaces, Banach spaces. Again, Banach spaces when it's considered, so when the maps are just bounded maps. And you can, other topological categories of topological vector spaces. And you probably can think, A modules of a given, over given rings, over given ring. So lots of nice examples. And okay, I already gave this exercise before, but now it gives the answer again without the proof. So in each of these cases, the addition structure is basically the addition on the values. Yeah, so you have two morphisms, you apply them, you add the values, you get new morphism. Okay.
Is there a way to make the object also monoid with this trick of using the delta map to gain like sum in a general
So you do
category?
have some. So whether they're monoid, it's a little bit more complicated question because one have to ask. So you should not think about the collection of all objects as a set. So you probably should not ask whether they are monoid. You can ask whether the isomorphism classes forms a monoid, and the answer is yes. And you can ask whether the category is monoidal category, which is a notion that we didn't define, and the answer is also yes. Whether the collection of objects is monoid, so the it's too naive question, and the naive answer will be no, because it's not associative, like in vector spaces. The direct sum is not associative on the nose. We think about it as associative. It's associative on the level of isomorphism classes. It's even much better than that. It really wants to be associative, but it's not associative by itself. We will discuss it later in the course what does that exactly mean.
You need to prove while you have semi additive, you need to prove that you have inverse and associativity, and unit you don't need.
So you talk about
No, I mean
this exercise.
No, I mean about the definition of abelian category.
I
When you
didn't
have a
get to this
semi.
definition yet.
Okay,
I'm
so
only
where are
defining
you?
what is additive category.
For an additive category, yes. So you need to prove, in order to prove that it's a group, you need to prove associativity and inverse. What do you need? Associativity is given or not already?
In order to prove that what is a group?
Is associativity is
Yeah,
given in
it's not
the
given, it's an
semi-simple?
exercise. I
Okay.
wrote it here. You have to, there is an exercise to prove that the addition gives a structure of a commutative monoid. It's commutative, and you have associativity, but you do not necessarily have inverse. And if you have inverse, you don't need to prove it. You have to prove it in the examples. Yes, it's not something to do it in general. So another exercise was to find an example of semi-additive category which is not additive. There is such example. Okay. Can we continue?
Yes. Yes.
Good. So another exercise. No, sorry. So now I want a billion categories. So before I want the notion of kernel. So suppose I'm already living in additive category. You can make this notion makes sense for any category with 0, but it's better to talk about it in additive or semi-additive category. You have a map between x and y, and you want to define its kernel. So its kernel going to be a sub-object of x. I didn't define what is sub-object. I can define in a moment, but it's some object together with a map to x at least. And what can I'll say about the kernel? The decomposition going to be 0. And the kernel should be somehow the largest thing like this. So it means that for any k prime, a map like this, it factors through here. Okay, so you see that this is already an initial object somewhere. In fact, it's probably, yeah, it is a limit somewhere. I can even write it as, it's even better than a limit. It is a fiber product, I think, yes. Yeah, so let me write that the fiber product. I think it will be even nicer. So kernel phi. Here you want all the elements in X that maps to 0. So you can consider that all pairs, element in X and element in 0, which is just 0, which map to the same point. So it's 0 times X over Y. When here you take phi, and here you take the isomorphism. Okay, so exercise. Verify that kernel is kernel in all examples. So you're familiar with the notion kernel in many examples, so verify that it works. Okay, so now the parties begin. So definition, co-kernel is kernel in the opposite category. Again, example, compute co-kernel. And the hint here that it's, maybe you're familiar with this notion, so it's a notion that you know. If not, then it's a quotient by the image, basically. And now, another definition, image equal to the kernel of the natural morphism between, so image of phi, so we have x, y, and phi. So we have natural morphism between between y and co-kernel of phi. Yes, because we had a natural morphism between the kernel of phi to x, so the dual picture will be from y to the co-kernel of phi. So this is the image, and co-image is the image in the opposite category. So let's write what is a co-image. Is the natural is a co-kernel of the natural morphism between the kernel phi and y. And now there is a nice thing, exercise. What?
2x, right?
and XU, right? Let's see. So we have kernel phi x y co-kernel phi. And now here we have the image of phi, and here we have the co-image of phi. Now I want to get map between one and another. Let me see how I do it. So the image is a kernel. Okay, so first of all, I want to get a map between the co-image phi and y. So yes, so this is co-kernel of that map. So I claim that there is a unique. Okay, maybe I'll just sum it up. I claim that the. Oops. Right. Again, the red trick. So the exercise will be that the unique. The red arrows exist and unique such as the diagram is commutative. So there is a natural map between the co-image and the image. So let's do some example because it's too confusing otherwise. So kernel is just a kernel. Image, let's talk about a billion groups. Yeah, so kernel is just a kernel. Image is just the image. Yeah, so it's a, because we said that the co-kernel in a billion group is a quotient by the image. So an image of a kernel of the quotient map will be what you quotienting by, what you quotienting by, which in this case will be the image. So kernel is, so image will be just the image. What will be the co-kernel? The co-kernel will be the quotient by the kernel. And sorry, the co-image, the co-image will be the quotient by the kernel. And you know that in a billion groups, you have a natural map between the quotient by the kernel and the image. Or in fact, it's not just a natural map, it's a natural isomorphism. So in a billion groups, you get that this map is isomorphism.
Rami, should not the co-image should have arrows reversed? Because this is the universal downstairs, the universal property of the image, if I'm correct.
Co-image. So what is the problem? There are several arrows. There is one arrow that goes inside
From
it and one
X
that goes
to
up.
the arrows from and to co-image phi should not be inverted.
The blue arrow or
the top arrows. The top arrows to co-image from X
arrows.
From X to co-image phi and co-image phi to Y.
So let's see. From X to co-image phi. So we say that co-image. Let's start with the image maybe. We say that image is a kernel of the map to the co-kernel. So the arrow is correct. Now from X to co-image phi, we said that it's the co-kernel of the map from the kernel. So we have a map to the co-kernel. So the arrow is correct.
Okay. Nice.
Yeah, I claim that the red arrows exist and unique, and I'm wrong, of course. I should be, yeah, I should put another condition, of course. I will put it in blue. Yeah, it's in blue. You want this composition to be 0 and this composition to be 0. Then those maps exist and unique. By the way,
This
the other
composition
compositions
should
are
be
automatically 0. Yeah, the other are automatically 0. This is not a new information, but those two it depends on the red arrow, so I put this condition, and then the red arrows exist in unique. Basically, then this red arrow is unique, and this red arrow is unique, and after you fix those two red arrows, then you can also get the vertical red arrow.
Isn't always they are zero? The map from kernel zero, phi to image phi?
Yes, because by definition, the image phi is a co-kernel of this map. And let's do the other example. So image phi by definition is a kernel of this map. And by definition of kernel, this composition is zero. So this proves that this composition have to be zero.
No, but also from kernel of phi to image phi.
To image, no, it's just not. So to co-image, from kernel to co-image, I have to be zero by definition. Because just dual to this situation. To image, it depends on the red arrow. So I demand that it will be zero, and then the composition is zero. So after this exercise, we go to the natural map. Let's give it some name. I don't know. Alpha, care. Bad name. I don't know what name to give it. From not care, co-image. Co-image. From co-image to image, yes. So from co-image phi to image phi. And now we can finally give the definition of abelian category and additive category C is called abelian if one, it admits kernels. This is called AB1 in Grothendieck's notation. It defines the notion of abelian category. So AB1 exists kernel, AB2 exists co-kernel, and AB3. No, I'm wrong. AB1 exists kernel and exists co-kernel.
Aren't those AB1 and AB1 prime?
Maybe I remember that it's one, but I never saw it anywhere written, so just people told me, so I might be wrong. Anyhow, AB2 AB2 this alpha co-kernel kernel is isomorphic. Yes, so in abelian groups, this second condition, AB2, is the first isomorphism theorem. That the natural morphism between the kernel and kernel is between the image and co-image. Sorry, between the co-image and the image is an isomorphism. And in general, this is a condition. It's not always true. So exercise, find example for AB1 not imply AB2. So I will give the solution. The answer is banner spaces, for example. And this is confusing example because, okay, the first glance you think you have the image. Okay, no, maybe I will say later why it's confusing example. Because another exercise, prove that if C is abelian, then and we have some morphism phi such that kernel phi equal to 0 and image phi equal to, okay, phi from x to y, Yeah, so kernel phi equal to 0, it's 1 to 1. And in fact, it is equivalent to one of the definition of morphisms. Image phi is equal to 1, it's to y is equivalent to one definition of epimorphisms. In fact, I think in this case, just monomorphism and epimorphism. So if it's 1 to 1 and onto, it implies that phi is isomorphism. And in Banach spaces, this condition seems to be satisfied, but it's not. You are right. Okay, seems to be satisfied, but it's not, because so there is very nice theorem in Banach spaces. You've probably heard of it, Banach open map theorem, that says that if you have a continuous map which is onto, then it's also open. Which means that if it's onto and one to one, then it's invertible. So it's always invertible as a linear map, but it's not clear that the inverse map will be continuous. And Banach open map theorem says that if it is invertible as linear map, then it is also invertible as Banach space, as a continuous map. So naively, I would think that if it's one to one and onto by this definition, then it should be isomorphism. But the funny thing is that the notion of kernel in Banach spaces, the notion of kernel in Banach spaces is the same as the usual, as the categorical notion, but the notion of image is different. So usually when you talk about image in Banach spaces, you just mean a subspace of the target. But then you see that the subspace is not necessarily closed. And if you consider the subspace together with, how do you call it, topology mushret, how do you say topology? Induced topology, you get something which is not a Banach space. So it cannot be the categorical notion of the image. And it turns out that the categorical notion of the image is a closure of the set theoretical notion of the image. And the fact that you have a morphism with a dense image, of course, does not imply that it is an onto morphism. By the way, the notion of co-image is exactly the usual image, but not with the induced topology, but with a quotient topology. And this is always a Banach space. So you have notion of co-image, you have notion of image, you have morphism between them, but it's not necessarily an isomorphism. It's a dense embedding, but not necessarily an isomorphism. Okay, so I think this is it, more or less. Any questions? No questions? I'm good. So Guy, do you want to stay for a couple of minutes to discuss the exercise? Okay, so see you next week.
Thank you.
Thank you.
Thank you.
The recording just.
Thank you.
Thank you,
Yeah, I will
Shabbat.
stop the recording. Good idea.
So-